Alright, we've done 2 ice table examples so far. Let's see if this third one brings anything to the table, anything new to the table. We have a sample of gas. It looks like it's the only reactant, and it decomposes according to the reaction below. We're only going to start out with the NO2 gas. Let me, in purple, circle everything that's given that's important. Uh-oh. They don't tell us actually how much gas we start out with. Alright. It comes to equilibrium. At least we know it's going in the forward direction, because once again we have no products at the beginning, and we need products to set up the equilibrium. And actually the equilibrium constant is greater than 1, so we should have a lot more reactants than products than reactants. Anyway, they let this come to equilibrium and they found out that the partial pressure of oxygen is 0.25 atmosphere. What are the equilibrium partial pressures of NO2 and NO? Very interesting problem. We have also this is unknown. A little worried, but let's do this stepwise. You know that first we need to establish the direction direction the reaction will go towards. It needs to make products. So we're going to conclude that it goes to the right. Or you could say that it's favored to the right or favored to the products. Okay. I'm not going to calculate the QP, right, because we're now working with partial pressures. We know that QP is 0 because your products are 0 at the beginning. So we need to make products. Let us go ahead and set up the ice table, and honestly, this is a very interesting problem, and I'm kind of curious to see, do you know how to set up the ice table? What numbers would you plug in? Let me get the first row started, or the reaction row started. Everything is a gas, so I'm not going to worry about putting the phases. But now we're going to be working with partial pressures. And partial pressure, when everything is a gas, is directly proportional to the amount. So we're just going to treat it like an amount or a concentration. They're all proportional. So we are going to use this number, 0.25 atmospheres. And let me fill in one blank. That 0.25 atmospheres is an equilibrium partial pressure. And I'll just put a little reminder here that we're putting numbers in here that represent atmospheres. That number, 0.25, will go here. 0.25 atmosphere. And the other number that may be helpful is this one. Start out with 0. Can you figure out the initial, the change, and the equilibrium concentrations? The hint is there will be one variable. We'll call it x. Okay, that will show up in several of these spots. Why don't you pause the video, take a look again at the problem, and see how many blanks you can fill in based on our problem. Okay. Well, because you go from 0 atmospheres to 0.25 atmospheres, we know that we added plus 0.25 atm. So we have the change. In the first 2 examples, our change row had the x's. Not in this case. we know exactly how much was added to the O2. Now, a trick that I showed in the last video was, go ahead and write that 1. That 1 is explicit or implicit? Implicit in this expression, 1 times 0.25, because that's going to help us figure out what the change for NO is. Because every time actually a molecule of O2 is made, 2 molecules of NO is made. So, and I said is made, so it's going to be plus 2. How do I want to write this? Times 0.25. And again, that 2 comes from the coefficient. We also started with 0, actually, NO at the beginning. So now we know this number it's 0.50. No variable. We know for a fact that this has to be 0.50 if this went to 0.25. Can we fill in the column for NO2? It looks a little strange, but I'm going to put X here. We don't know the initial amount. Okay, we just know that at the beginning the whole flask is filled with NO2 gas. But what can we fill in for the change? Look at that, the same coefficient. But now we're losing NO2. We're losing reactant. Here on the right side we were gaining product. This is why we're going to put a negative sign. And then how much? 2 times 0.25. Again, we are using the coefficients to remind ourselves how to multiply this change. If we set the change of this oxygen to 0.25, which we are. So be careful. I was about to write here negative 0.50, but it's x minus this. So we have an initial amount x, and we're removing it, or we're consuming some of it. And yeah, we could definitely put here 0.50. Okay, but don't forget the x. Don't forget the x. That is the ice table. I think that will get us to the answer. What we're really looking for, right, is the equilibrium partial pressures for all of them. Oh, we already have the one for NO. We already have that one for NO, and we were given the one for O2. It's this NO2 that's the mystery. Step 3 in the previous two problems was to set up the equilibrium expression. Just be aware that it's now a KP. Partial pressure. So several terms are going to be squared, and it's not concentration, but partial pressure. Okay, I know some students again would rather just plug in the numbers right away, but I would be afraid of missing the exponent. I almost forgot the O2 as well. PO2. Okay, and then on the bottom we have partial pressure of NO2 squared. Yikes. Okay, let's fill in the numbers. Well, we actually do have numbers for the numerator, right? NO is 0.5 squared. I'm just plugging it here. Should I write it out? Maybe I should write it out. 0.50 squared times 0.25 divided by x minus 0.50 squared. I want to try to avoid having to expand this, because I don't want an x squared term. Although the numerator is pretty clean. We could actually get a number for the numerator. Oh, and all of this actually is equal to, where are we? Oh, here it is. Oof, almost didn't see that. 158. 158. So what can we do? Um, let me simplify this numerator. 0.5 squared equals times 0.25. So on the top we have 0.0625. At the bottom denominator we have x minus 0.50. I'm not going to expand this just yet. Equals 158. In a previous problem, I think it was example 2, we took the square root of all the terms, and that was the proper way to do the algebra. We could do the same thing here. We could square root, because we want to get this as x minus 0.5. We don't want this squared. It will just complicate matters. So square root of a square, right, would give us the term, and then we just square root everything else. Do the same for every term. Okay. I already have that number saved. This answer. So we have 0.25. The denominator is now x minus 0.50, and our numerator, not our numerator, our KP, 58, okay, 12.56. I don't want to round to two little digits right away. Okay, cross multiply. 0.25 equals 12.5698x minus 6.2849. Solve for x. We're going to bring this 6.2849 to the other side, plus 0.25. And then we're going to divide both sides by this number here, divided by, oh, all the way at the bottom, divided by 12.5698. Okay, x equals 0.520. Our ice table is in atmospheres, so that x will be in atmospheres. ATM. And then finally, we're going to plug in that x up here. Ooh. This is good news, because freaked out a little bit there. X is 0.520 minus 0.5. So we don't have a lot of it actually left over. We have 0.02 atmospheres. The partial pressure, this is all at equilibrium. Partial pressure of NO2 equals 0.02 atm. And we have, so we have our numbers right here already. Here, here, and here. For the NO, equals 0.50 atm. Running out of ink. Okay, and then for the O2, partial pressure of O2 equals 0.25 atm. You could always double check, right? You could always plug in, what is it, this partial pressure over here, and these two up here, and double check if it equals 158. I did this previously, and my answers look good to me. Circle. Is that all I want to say about this? You know, we don't have a lot of the starting material, the reactant, because it is um, it is greater than 1, and it's 1.5 times 10 to the 1. Is that right? 1.5? No, 1.5 times 10 to the 2. Okay, good. That was one where we used partial pressure, and that was one where the x was actually in the initial line, and we were able to get a number for every term in the change row. We hadn't seen that before.